Oh yeah, sorry. Oh, you're gonna borrow that? Okay.
Yeah.
Okay, anyway, so let's start for today's lecture. So on Monday, Ram talked a little bit about multiple testing. And today's lecture, I'll focus on differential expression analysis. And so there are two portions of today's lecture. One is differential expression analysis. The other one is gene set analysis. There's a downstream analysis follow the differential expression. So we want to identify differential gene expression so that we can identify gene whose expression levels are associated with a response or covariate of interest. Covariate of interest could be some clinical outcome. A response could be clinical outcomes such as survival, response to treatment, or just or simple like a classification, right? And covariate could be treatment, dose, times, and etc. And we want to assess the to identify differential expression will be done by testing. So this would be to assess the statistical significance of the observed association. So usually people, a quick way would be just look at the fold change, right? But fold change is just like a quantifying the magnitude of the difference, but you need to have a more definitive way to assess difference that would be done by statistical testing. So the input data for differential expression analysis for microarray of RNA-seq would be usually a matrix of pre-processed log intensity gene expression value. Okay, so it comes with rows for genes and columns for sample. We always assume this matrix is already pre-processed, properly pre-processed. If not, you need to normalize the expression value, transform the expression value, and then start your analysis. Otherwise, garbage in and garbage out. Okay, make sure this is like properly.
So for RNA-seq data, you also do log transformations?
If you use Lima, yes, it is a log transform. But remember we talked about normalization a few lectures ago. So depending on which software package you use, when you're really doing the analysis using R, you don't really log transform it. The thing you feed the package depends on which package you use, but usually it will be the raw count matrix.
Okay.
But the software, the package, it will take the raw count matrix and perform the internal normalization, like with a few lines of command. No, it doesn't do it automatically, but you need to kind of tell the software package which normalization.
Some option.
Yes, some line of code telling it we want it to normalize the data.
I guess my question is, the RNA-seq is count data. They treat the RNA count as intensity data log transform it.
No, it depends on the software package. Yes.
Okay.
It treated as a count, but still they want to kind of normalize the data before running any statistical analysis.
Because I have received the data set and it was normalized using scan, single array channel.
Okay, the scan. That's normalized with respect to what?
Like exon level. It was normalized at the exon level, and it's like, I read a little bit about it, but they were saying the single channel array normalization, what it does, it actually corrects because if there is multi-center data, it's also correct for multi-center and also corrects for the time and all those things that could affect. But I couldn't really, I tried to read them.
But that's not correct for the
RNA-seq.
Yeah, the technology itself. So the normalization So you say you use the scan that package or
No, I already received the data. Used
okay.
like that was a Decipher data. It's from a Decipher. So Decipher actually gets this expression level, and the expression level is normalized using scan. I wanna, at some point, I want to get the paper and read a little bit more in detail to see what the scan does.
Yes.
But it's on the exam.
But I think the scan is the software. According to my memory, it's more of like correcting for kind of like a batch effect type of
batch effect.
Yeah,
Correct.
so
it does have a batch effect. Yeah.
Yeah, so the batch effect you could say it's a time effect. It will be a more center effect. They can be all called batch effect.
Okay.
But that does not correct for like the internal the thing that we need to adjust for the RNA-seq. Remember we have different gene length and we have
and position
the distribution RNA distribution type of thing. So but this is RNA-seq. So for DNA, we probably don't need to do that, or it really depends on what you.
Yeah, I got the data processed. I can't do anything about it. I don't have the raw data at all. I just have this data already processed given to me.
Yeah.
Maybe I'll show you when we go back how the data.
Yes. So so make sure what you get is kind of like properly normalized QC corrected for batch effect. Then you perform all the next step, the differential expression analysis. So there are actually two major components when we try to identify differential expression, differentially expressed genes. One, the first step would be we select a statistic which will rank the gene in order of strength of the evidence for differential expression, right? From strongest to the weakest. So we always say doing a test, t-test, things like that becomes, this is actually like a select a statistic. And the second step would be to choose a critical value for the ranking of the statistic about which any value, above which any value is considered to be significant. So this is kind of selecting a threshold, a cutoff threshold for claiming significant. We all know the 0.05, but because they're like, it's not just like the p-value 0.5, we should look at the corrected p-value because of the tens of thousands of genes for testing. And also, not just the p-value, we should look at the fold change as well. So it's always, I shouldn't say a critical value, it should be like a set of criteria, a combination of critical value actually for the ranking of statistics. Look at the fold change, usually it should be the absolute value of fold change and the corrected p-value.
They use that for a volcano plot. That's kind of almost the same.
Yeah, the volcano plot. Yeah, I'll talk about that. So here, in terms of select a proper statistic, that's the proper statistical test. If we do a two-sample t-test for each gene, right? This is like a statistic t-test statistics for a two-sample t-test. Very standard one. Assuming the pool variance. Okay, so this is just like some mathematical formulation. But the thing with the testing using standard t-test is when we have very small sample size, it could lead to unstable estimate of variance. Because by chance, there are some genes have very small variance, even if they're different is small, very, very small, but the variance is very small, almost like no change. And by doing this test statistic calculation, you have a small value at the denominator that could make your test statistic huge. But in fact, it's actually not much of different. And also, we would not be interested in those kind of genes, right? Then that would result a large t-statistic and very significant p-value. But in reality, If you look at the fold change, it's just almost like 1, right? The ratio, the fold change. And then also sometimes data are not normally distributed, for example, RNA-seq. So if we use t-test, that's not correct. The p-value is not correct if we use t-test. And also there's some multiple testing issue. One way to get around this issue would be to use non-parametric tests. That means we don't assume any distributional assumption for the expression data. There are software packages that use non-parametric tests. For microarray data, there's this SAM software. That's the significant analysis of microarray, and it's the SAM stand for this. And then also the equivalent package for the RNA-seq data called SAM-seq. But we don't, one thing with the non-parametric test is it has low power when you have small sample size. So you need to have at least 10 replicates in each group for non-parametric tests to work well. Okay? But in many situations, especially the pilot study, the type of data, you don't have more than 10 samples in each group. And also, non-parametric tests, you only work well, you have 2 groups, right? When you have multiple groups, then you do a cross-coalesce. It's an ANOVA type of equivalence. But then, what's the next step? You still need to do pairwise comparisons. And for non-parametric tests, you cannot adjust for covariance. So that there's no sophisticated modeling structure because it's not model-based, it's just distribution-free. So you don't have a framework for accounting for covariate adjustment, for accounting for like a correlated structure of the data. So that's another drawback of using non-parametric tests.
If the sample size is very small, even if you want to do the modeling, that's still...
Yes, that's so if you have very small sample size, you don't even do modeling, just as simple to sample.
If the sample size is very small, non-parametric or t-test, what would you recommend to do?
A parametric modified t-test.
Still do modified?
Modified t-test, yeah. I will not do non-parametric. Well, at least 7, I would say. 10 might be too many, but at least 7. 7 is the magic number for non-parametric test. 7. You need at least 7. So this is a non-parametric test. For parametric method, there are a few common software packages. One is the Lemma package. That stands for Linear Models and Differential Expression for Microarray Data. So it was first developed for microarray data, but they keep adding on components, and now you can also use it for RNA-seq data. And there are 2 other packages, commonly used packages for RNA-seq data. One is HR, and the other one is DSeq. And now they have the second, generation DSeq too. But they are all built on the same foundation. So for Lemma package, this is one of my favorite. So it has for the distributional issue, it can be solved by variance stabilizing transformation in this is for RNA-seq data. For microarray, it doesn't have any distributional issue because it was first developed for microarray data. So it just takes the log of the expression, the log intensity. Okay. And for the variance estimation issue, so the variance estimation issue is this issue. With small sample size, you get a large variance estimate. But Lemma cleverly take care of this by kind of, I mean, if you're interested, you could read the mathematical detail, but the key idea is it kind of like use all the information across all the gene to estimate a common, well, I wouldn't say a common, but to estimate gene-specific variance. And it makes all the variance for each individual genes to be shrunk towards the mean of all variances. So that means for all the large variants, it will get smaller towards the mean of all variants. For the, so that will alleviate the large variance small scenario. Oh, it should be very large variance scenario. Sorry, this is a typo. Very large variance scenario will be alleviated. Sorry. It's very small variance scenario, very large test statistic. Mm-hmm. Yes. Okay. So the idea is to make the small variance a little bit larger and the large variance a little bit small. Kind of meet in the middle ground. Okay. And this is called a modified t-test. And for the multiple testing issue, Lima would report the Benjamini and Hodgberg corrected p-values. You could specify other options, not just this option, but this is a default one. Okay. And the good thing about Lima is it could the simplest one would be compared to group, right? But the good thing about Lima is it could handle very complex study design. So when you have several other factors to covariate to control for, this could be done in the linear model framework by specifying a design matrix. Remember in our, I don't know, the linear algebra or regression class, we talked about the design matrix for the linear model. Remember that?
I do. But in the linear is actually is none of the classes they offer. It is actually in the design class. They never give it to the master's program.
Oh, really?
Mm-hmm.
Okay. But if you take, I think any generalized linear modeling class, there would be a design matrix. So the design matrix is where you have this covariate component adding on and the interaction term and the intercept and things like that. Depending on the coding system, you could use like a reference coding, you could use a Spelling coding and things like that. But you do need to know a bit about the linear model to specify the design matrix in order to use the lemma. Yeah. But for two-group design, it's very simple. And then Lima will generate this design matrix for you. Okay? And we will demonstrate this in our lab session. Different, coding, different coding selection by specifying this. And in terms of performance, Lima controls type 1 error rate correctly. Type 1 error is the alpha level. And it has very low false discovery rate. Okay, we can see this in an example given later. And has the best, and it's also very powerful. It has the best power among methods that correctly control type 1 error and false discovery rate, which is nice. And another one is computational speed. It runs much faster than other differential statistical methods. All right, so this is the lemma. So this is basically based on like a Gaussian distribution, this method. And another two methods, the RNA-seq and HR, they are methods based on count. Okay, and the relevant distribution for count data, there are three distribution. One is the binomial distribution. The other one is the Poisson distribution. So these are all discrete distribution related to count. not continuous data. And then the next one is the negative binomial distribution. So I'll kind of like walk through this briefly, because initially the RNA-seq data, it follows a binomial distribution. Okay, so it comes from this, because for each gene, the probability of getting exactly K-map read count out of n total read, it follows a binomial distribution. So this is basically the definition of the binomial distribution. Okay, and so we can write out the probability mass function for a binomial distribution. And then if the number of read is big, so you imagine that it goes to infinity, which is true for RNA-seq data, right? We get millions of read. And the probability of a read getting mapped to a given gene is small, which is also true, right? Then this binomial probability mass function can, after you take in the limit and things like that, it can be approximated by a Poisson distribution. Okay? Yeah, this is kind of like a college algebra.
Yeah, it is.
Yes. But anyway, just take this as like a knowledge. We don't need to derive this. So binomial can be approximated by Poisson distribution if n goes to infinity and
P is small.
Yeah, small. Okay. So that's why the Poisson distribution comes into picture. We started from the binomial, and then now we have the Poisson. And now why we want to use the Poisson distribution, because it has a very nice property. The mean and the variance of the Poisson variable is the same. It is the same as the rate parameter lambda. Okay, this is a very nice property for Poisson distribution. But one thing with the Poisson is this lambda. Let's see the consensus. If we use Poisson distribution to model the RNA-seq read count data, that means the variance is lambda. But research has shown that the Poisson model is appropriate only for technical replicate. So if your RNA-seq data, they are technical replicate, you use a Poisson model to model it, that's perfect. But if they come from biological samples, then it would have extra variability. A Poisson model is not appropriate. And then the negative binomial distribution comes into picture for biological replicate because of this extra variability. For the negative binomial distribution, this is useful for count data when they have variance significantly greater than its mean. So we call this over-dispersed. So whenever you heard something like over-dispersion, that means the variance is greater than the mean. So for Poisson, because the variance and the mean, they are the same. But for RNA-seq data, if they come from different patient sample, the variance would be greater than the mean. Okay? So people find out this because it's very easy. You get the data and you just summarize the mean and the variance, and it looks like the variance is greatly larger than the mean. So that means the Poisson model is not appropriate. So that's why people think the negative binomial would be a good way. And for negative binomial distribution, the mean is lambda, and the variance is lambda plus this is the how to define this?
No.
Theta.
Phi.
Okay. Phi lambda. And then this phi is like if it goes to 0, it shrinks to a Poisson. Okay, so this phi is called the over dispersion parameter. And so negative binomial, that's why negative binomial distribution is used to model biological replicates. Any questions? So we started out with a binomial and then go through Poisson. The Poisson doesn't properly account for the variance estimate, then we continue to negative binomial. Okay. All right, so these two packages, the DSeq2 and HR, in these two packages, all the recount they assume to follow negative binomial distribution, and it parameterized by its mean and variance. So basically, it's the lambda and the phi, the over-dispersion parameter and the rate parameter. And then again, this software package did an estimate of the variance by borrowing information across genes. For two group comparison, they actually perform an exact test. So that's very similar to Fisher exact test. It's like an enumeration of a combination of the recount and then try to calculate the probability. But for a more complex study design, they can actually use also the modeling framework. But it's not based on Gaussian distribution, it's based on negative binomial distribution. Okay? And for differential expression comparison, it would be based on likelihood ratio test, because you can construct a likelihood function. So yeah, today's lecture is more like a technical thing. And then this is one paper kind of like comparing these packages and also Lima. So a quick summary would be Lima is based on developed first for microarray is assume Gaussian distribution after for all the log transform expression value. And in terms of normalization, Lima performed the default is quantile normalization. We talk about quantile normalization, forcing the distribution to be the same, but still preserving the rank of the data. For DSeq, it performs. Let's see, what do we see? Oh, it's like a relative log expression, relative log ratio expression. Yeah, you could go back to the slides to refresh. We talk about that. And for the HR, they perform trimming of n values. Okay, so that's the difference in terms of normalization. And in terms of statistical testing, Lima used modified t-test, adjusted p-value, the Benjamini Hochberg. DSeq and HR, they all use like a negative binomial distribution based test, exact test for a simple two-group comparison, likelihood ratio test if you have a more complex design matrix. Okay, and in terms of, in terms of performance, the actual gene set they identify, I would say HR is more lenient, like will give more differential expressed gene set than DSeq and Lima. DSeq is the most stringent one, the most conservative one. Lima is in between. So we let's look at this paper. This is like a comparison of method for different differential expression analysis of RNA-seq data. So this paper kind of like look at all these different type of software package that could perform differential expression analysis. And this figure shows the number of genes found to be significantly differentially expressed between the two mouse strains. So we will expect there are some difference between them, right? Let's just look at the three packages I talk about. One is the HR, one is the This room is Lima, and this is DC. Okay, as you can see, HR give more the most differential expressed gene, and then Lima follow this, and then DC the third one. So it seems like a smaller set identified by DC. But then, what about false positive, right? So this one, should make it smaller. So this is the average number of genes found to be significantly differentially expressed when we compare two subsets of mice from the same strains. So in which case we expect not truly differentially expressed, right? They come from the same strain. They should be same.
So this is like a false discovery, right?
Yes, false positive, yes. So again, because I want to make it larger. HR, well, forget about this. This is just not a good method at all. So we wouldn't even look at it, talk about it. So HR again give a higher number of false positive, right? As compared to Lima and DC. So it looks like DC give the smallest false discovery, has the best control false discovery. And then comes with the Lima. HR has a relatively weak control for false discovery. But at the same time, DC doesn't give, DC is not as powerful as Lima.
Yes.
So that's why in previous slide I would say Lima has a good combination
of power.
Yeah, of power and false discovery rate control. It's kind of like in between. So that's Lima is usually my to-go package when running everything. I'll do Lima first. If I don't find many genes using Lima, I might consider using HR to expand my list. Because it's just discovery. We always want to have some candidates to look at. But if I use Lima and I find too many, I might want to narrow down and I will use DC, also to use DC to see kind of in the setting to list. Well, in publication, we wouldn't say we do all sort of things and get in the setting. But for myself, like running analysis to get a good feel about the data, I will run Lima first to see if I get a huge list or small list. And
does the list of your discovery overlap between methods? How is the overlap?
Just to see that they share the common genes by using all three methods. If all three methods give the same set of genes, those would be strong evidence.
Yes,
they could be something worth looking at. Yeah, especially if you want to narrow down the thing. Yes, so this is usually what you get after you perform differential expression analysis. All different type of software package, regardless what you use, it will eventually spit out some outcome that looks like this. Okay, it's also like a matrix, and one is the rows still stand for each gene, and the columns here, usually the first column will be kind of like the average for group 1. Average, well, this is like a normalized intensity value. That's why you see some negative value because it's normalized, kind of centered around 0. This is for the second group if we have 2 group comparison. And this is the fold change on the log2 scale. And this is the actual fold change. And you can see we have positive fold change and negative fold change. But make sure you know the fold change is which group versus which group.
What is the first two? Is it a t-test, like a modified t-test, like a statistic?
Where?
With the group A, like for example.
No, this is just the average expression value for group A, averaging all the group A samples. It's like a mean.
For that gene. Okay.
Yeah,
okay.
the mean.
Okay.
The mean for that gene, yes.
Okay.
I wouldn't say every single software will spit out a result like that, but this is usually you will want to inspect after your analysis, at least to make sure your fold change is calculated correctly. So the fold change and then the p-value. So these are all like for individual gene they perform tests. P-value. So if this is from lemma, it will be from the modified t-test. If this is from HR or DC, this will be based on the negative binomial type of test. And then this is adjusted p-value. It could be the Benjamini-Hopper or it could be something else. Okay. And then when you get a selection of your gene list, you will want to look at the adjusted p-value or p-value. Sometimes you don't get any significant adjusted p-value after you do that. You might just want to look at the p-value and also look at the fold change. We want to take the large fold change one and also with significant p-value or adjusted p-value. So one way to visualize this would be using the volcano plots. So this is a diagnostic plot to visualize the differential expression testing results. And it's basically a scatter plot of the statistical significance versus biological significance, right? Statistical significance will be the p-value. And biological significance will be the magnitude of the change. That will be the fold change. And ideally, we will want to highlight the gene that would agree, meet both criteria. So this is the example volcano plot. The x-axis is the log2 fold change. Okay, this is a two group of patients, one with Aspergillus infection and the other one without Aspergillus infection. And the y-axis is the negative log 10 log 10 base p-value. So that would kind of like make it as an integer value. And the larger the value, the more significant.
Why there is negative? Oh, it's log 2 for the
yes.
change.
So it's kind of make it, because if you log a value less than 1,
Like
any logarithm of value between 0 and 1 would be negative value. So you want to flip it to make it on the positive scale, just for visualization. So the larger this value, the more significant. So we will want, and also the x-axis here, the further away from the center, the larger the fold change. So we would like to kind of focus on these two rectangle area and it will usually highlight, the dots with color in these two areas. And as we can see here, we get a
agreement.
The more, I would say, this is usually what we call the upregulated genes, right? Because it comes with a positive fold change. Upregulated, that's with respect to Aspergillus versus none. And this is the downregulated gene because it comes with a negative fold change. Okay, and here is just a raw p-value because I didn't find anything that was significant with adjusted p-value. But ideally, this should be the adjusted p-value. You log the adjusted p-value if you have anything. Any questions? The volcano plot. It's a nice visualization for your after you perform differential gene expression. And of course, like this p-value, the threshold 2 fold change is not always 2 fold change. You can move your this vertical bar if you use like 1.5, 2, or even 3, if you end up with too many. But definitely greater than 1. Okay. All right. So this is for differential gene expression analysis, and we'll have a lab session for this. We'll demonstrate using lemma, using DST, and using electron. Any questions? All right. So the second one would be the very precise. The next part, we'll talk about gene set analysis. So this is just a very basic introduction of gene set analysis. There's like a more complicated method being developed, and also better software than the one that I discussed here. But those software are usually paid software. You need to pay thousands of dollars each year for renewing the license. So if you really need it, you purchase it. But for the moment, we just use the interactive web available tool to demonstrate the idea of gene set analysis. So the motivation for doing this is we get a list of differentially expressed genes from microarray sequencing experiments, right? And next step, we would like to give this list of genes a biological interpretation. A reasonable thing to do is to rely on existing annotation to relate the selecting gene with some biological knowledge. So in terms of biological knowledge, the most important thing you want to know is probably what gene or their products are concerned with, right? Their functions and the biological process. Then we should, refer to annotation database for this type of information. So there are many different databases for functional annotation. One is a gene ontology, and the other one is a KEGG, and there are also the Bohr's molecular signature database. So there are many different bases. Basically, there are people, scientists, they curated this database, they updating it as time goes by. So adding new knowledge about all the genes they know about from all the publications and research. So in this database, several gene sets are annotated to the same categories by virtue of a shared biological properties, right? This is like a dictionary. The gene ontology is a database consortium that unifies representation of gene and their gene products across all species, not just for humans. So I think I will not go through this. It's basically, there are gene ontology terms. It defines all genes and gene product by the 3 organizing gene ontology domains. So it comes with 3 domains. One is molecular function. Which molecular function does a gene or gene product have? The second one is biological process. Which process is a gene involved in? And the third one is cellular components. What does the gene product X? Where? And I think usually people are more interested in the biological process or molecular function. And for cellular component, we usually like I said, the gene ontology is basically like a dictionary. You can look it up. So each geo term has a term name, which may be a word or a string of words, a unique alphanumerical identifier, a definition with cited sources, and a namespace indicating the domain to which it belongs. So if you find like a geoterm, it comes with this identifier and the name and the namespace. There are 3 namespace, and this belongs to biological process. And the definition of these geoterms, the maintenance of the structure and integrity of the mitochondrial genome, and things like that. Okay, it's like a dictionary. It's like when you look up a dictionary, it comes with the name and like pronunciation.
So if you have a gene name, you also can convert it?
Yes.
But you have to pay?
What?
You have to pay them to tell you
No,
what genes you have?
What do you mean you have a gene?
Like, for example, you know how you have, like, you showed that table that you had group A, group B, and then you had the name? You had a gene level, right? You had gene name or DNA name.
You mean a list of gene or?
Exactly.
Uh-huh.
So if you have the list of gene, can you go back and see where that gene works and where it exactly is on the DNA?
So it's basically in a gene ontology. For if you do a quick search by typing just the gene name or gene symbol, it will spit out each gene belong to what process and.
Okay.
But each gene will fall into many different categories. Yes. So there are almost 20,000 geoterms, with tens of thousands involved in biological process, just less than 2,000 involved in cellular components, and about 800. I believe this number is outdated. It grows now, but that's the idea. And the geoterm in each ontology has varying level of specificity. Okay, here is an example for the geo annotation. So here, each gene may be associated with 0 or more geoterm in a given ontology. Okay, so this is just one gene, and if you search it, this is one gene, and then you search it, it pop up in different annotation, different categories. So this gene involved in this process, this activity and this activity. But what we'll be using for this is not just looking at individual gene. We usually look at a set of genes to intercept with the category to see whether it's enriched. But then you can also click on individual gene to see whether it's involved in different categories as well.
Okay.
So constructing gene set from geoterms. So the set of genes associated with any particular geoterm could be considered as a categories or gene set of interest for subsequent testing. So we could simultaneously query many groups, general and specific, to better understand the impact of treatment on expression. Suppose we use this query to select interesting set of genes. What can we do about this set with microarray and RNA-seq data? So what we can do is to test gene set with gene expression data. Testing gene set with gene expression data, we get a subset of all genes chosen by some relevant method, like the modified t-test or things like that. And then we get a list of annotation, each one linked to genes. Say this will be the gene ontology. And then we can perform Fisher-set tests. Okay, this is just the simplest way of doing gene set analysis. And this can be done in David. This is abbreviated from the Database for Annotation, Visualization, and Integrated Discovery. So David, is that here? Oh, this is the website. You can just like in your web browser, you just type in David NIH, and the first link will be this. Okay. The method with the Fisher-set test. So first, we select a short list of genes that are declared significant. So that would be your differential expression gene. And the intersection of the selected list and the functional category is then evaluated by Fisher test to check if many more selected genes than expected belong to that categories. That would give us the p-value. A simple hypothetical example. Suppose we have 30,000 genes, in human genome background, and 40 of them, they are involved in p53 signaling pathway. Okay, so 40 out of 30,000 genes belong to that particular signaling pathway. Now we perform an RNA-seq experiment. Okay, and we get a gene list of 300 genes, differentially expressed gene, 300 of them. And we found out 3 out of 300 genes belong to this signaling pathway. So out of these 300, there are 3 genes that belong to this 40 gene that involved in the signal pathway. Then we want to ask a question, if 3 out of 300 is more than random chance comparing to the human background of 40 out of 30,000, right? So it's more frequent occurrence than the background.
That's the Fisher test.
Yes. So that's why we want to perform like a Fisher test. We can construct a 2x2 contingency table with here will be the human genome, right? We have 300 genes out of we have 40 genes out of 300. 30,000, sorry, out of 30,000. And then here is our differential express gene, 300 differential express gene, and 3, they are involved in this signaling pathway. Okay, the null hypothesis is our gene list, this 300. Gene list is a random sample from the population.
It's not.
Yeah, and the alternative hypothesis is something we want to test. It's more p53 signaling pathway genes than expected from our gene list. So we perform a Fisher test and get a p-value of 0.007. So the interpretation of this test will be, we say the gene set involved in p53 signaling pathway is enriched, which is actually overrepresented in our gene list from this RNA-seq experiment. Okay.
On the other hand, this pathway is also associated with this outcome that we're looking at.
Yes. And also like the differential expression analysis, there's a multiple testing correction involved here, because a gene list obtained from the experiment, we will be intersecting this list with many different functional categories, right? It's not just so if we get this gene list of 300, we look at the p53 signaling pathway. This is just one category.
Correct.
So there are so many other different signaling pathway and biological process. So that would involve performing multiple Fisher tests, many of them. So we also need to correct for p-value. Again, we can use Benjamini-Hochberg false discovery rate method. So this David software, it does multiple testing corrections, but it only does that for each category, within each category of gene set. So if you have like a biological process, it only do within the biological process category. It won't consider the molecular function of cellular process. Okay, so adding more category does not change the FDR. So be careful how you report this number. So you should know it's corrected within the biological process, not across all the functional categories. So this is here is a short demonstration for using David. So once you click on the link and go to the website, first, can actually demonstrate here. So NIH David, the first link is this. So this is an interface for David. We could go to the left hand, there are like a panel. We pick the functional annotation. And here you can copy and paste the list of genes from your analysis. Or you can kind of upload it. You can copy and paste and you can upload it. And then also select an identifier. So this is the platform we use for, because if you do a microarray experiment, the list you obtain will be usually a probe set. So it comes with a specific type of identifier. So you need to let David know what type of a platform you'll be using. Or the simplest type is if you know all the gene symbols, then you can select gene symbol here. Gene symbol. Or gene ID, that there's a way where where is it? There should be. Oh, right here. You got this gene ID, you know. Gene ID, gene ID, gene ID. But David is quite smart. Usually it could identify for you. If you pick the wrong one, it will tell you. So select it, and then the list type here is a gene list of background. So we should select the list type, gene list. This is what we for the input. Okay, and then we could use a demo list here. So the demo list is for human background, and we select the species. Okay, and then use this for demonstration. And then here is the annotation summary result. And we will uncheck the default. So here you see there are many databases. You could just think of these or different databases, okay? And if you expand this, these are all different built-in databases, annotation databases available in David. For example, if we want to just do the gene ontology, you see here as like there are so many versions and different category. But the red color, the highlighted one, is the most like the common one that people would pick. So this is the biological process. Okay, we can select this one. And this is the cellular component. And this is the molecular function.
So you can choose more than one. It's not just
you can choose more than one, and you can just pick one at a time and look at them.
Okay.
Because the false discovery rate will not only correct for the biological, all the category within the biological process. So adding more will not change your adjusted p-value.
What does the percentage number? What are those percentage numbers?
I am not sure. I think that's something that it covers the percentage of all the genes, or it covers the percentage of all the categories. There are menus, help and menu. I think that explains all this. And the pathway here, if you look at pathway, there are different pathway database, and then these three are the common ones, and we can pick, the KEGG pathway or the reactome pathway as well. I think the percentage here is like the coverage of these dictionary is I encourage 91.7% of the genes or things like that. And then once we select this functional annotation chart. Okay. And it will give you things like that. Yeah, it's quite overwhelming. So that's why I prefer to pick one category at a time. Let's go back. Unselect. To remove all this, it's just too much information going on here. Okay, so now we only have the biological process selected. And functional annotation chart. Okay, now as we can see, there are 145 genes from that demo list one. And then this set of genes, they are enriched in this biological process. The geo term corresponding to this biological process is defense response to fungus.
Mm.
So this will be the, what is RT here? Functional related term. Oh, okay. It's gone. Sorry. I'll do it again. And this count number is 5. So that means 5 genes out of this 145 list belongs to this category, like this defense response to fungus biological process. It belongs to the biological process. And the p-value is the Fisher-Isaac test p-value. And Benjamini and Hartford adjusted p-value is within all the biological process after adjustment. Okay? And it goes on, and this list is not very enriching in any of the repeat biological process. We only get one adjusted p-value significant. Anyway, let's look at the pathway. Sorry, real quick. So I select the KEGG pathway and I click the functional annotation again. So if we look at the pathway, this gene list is enriched in pathway in cancer.
Is it?
None of the
Yeah, but what is the p-value?
P-value, well, adjusted one is not significant, no. But the unadjusted one is 0.01. Not bad. I mean, if you want to talk about something, you pick one or two to talk about it. Yeah. So this is just a demonstration how you use it, and you can download the file by clicking here.
That makes a lot of sense.
Yeah, it's kind of like a basic gene set analysis tool. But if you want complicated, sophisticated thing, you probably want to look at the IPA, ingenuity pathway analysis. That's a paid software, and it can produce very fancy analysis and very beautiful figures.
Okay.
Yes, but this is good for practice.
We should get our oncology department to buy this software and let us use it.
Well, I know researchers, they buy their individual license, but unfortunately UCLA, they don't have like a site license. It's very expensive. I think that's the business model this software runs. They want individual license purchase and make a lot of money. Okay, so this is for gene set analysis. Any questions? Okay, that's all for today.
Thank you.
Thank you. Oh, and then I'll give out the paper quickly list. Right. Because I think we have actually 7 people. 7 people. I'm thinking, and we have 3 lecture time allocating for paper critique. I'm thinking maybe we should do each person get 1 paper and do it instead of working together. Yes, because otherwise there would be only 3 paper, and then in 1 lecture time,
So what we do
talking about 1 paper is just too long.
Can we do 2 papers where we work it as a group? Because I think it's kind of one suggestion you had that.
Yeah, because
like
I want to have more
medical.
variety for paper. 3 paper is just not.
Yeah, I don't want to
Have the
present at least.
have the
I
medical,
can...
have a medical, background.
Yeah,
kind of
I do
statistical
want you to work as a group, but talking 1 paper, 1 hour talking 1 paper is just too much.
How about, I don't know, each group do 2 papers?
Each group to yeah, I think that might be a good idea.
What do you think?
Yeah.
I'm okay either way. I mean, I don't like.
I mean, if we only talk about 1 paper in 1 lecture, I think we just.
I like the idea of working a group, but then having to do 2 papers is like a little bit more work. So I don't know. I'm okay either way.
But each
We're working on 2 papers too much work.
Could be.
Yeah,
Yes, we
that's
have
the
to
only
research
downside
the
of
two
doing
paper.
two papers with the
That's true.
group. So
Yeah.
we'll have to.
But individually, each person do 1 paper. That's a lot too.
Well, but at least you don't have to read in depth. Each person would have to read in depth
Yes.
both papers.
Okay.
To do it that way. So it will be more work, but it's kind of fun to work as a group. So I don't know. I'm kind of like both has pros and cons. So I don't know. Whatever you guys want to do.
If doing individually, that's not bad. I don't know. I'm not sure.
I can do it.
So, what do you think?
I don't know. I would prefer just 1 paper. 2 paper in-depth reading, that
Might
too
be
much
a lot.
So we still do 3 paper, like 1 paper for each lecture, but more in depth.
More in depth.
Review.
Yeah.
Okay.
Yeah, that's fine.
And if we finish before the lecture ends, we just go.
Okay. If you're happy with that arrangement, that would be less work for everyone.
So we'll be like this.
Still stick with the original.
Three groups.
3 group. Yeah.
Each group 1 paper.
Each group 1 paper.
I'll bring my paper. I don't know if my paper is appropriate, but I'll bring my paper suggestion, the one I was reading before, next time, and I'll give it to you to look at and see if it's appropriate or not. And if you like it, and if not, then
I'm happy with anything.
Yes, me too.
I have too many papers, like I just reading.
Yeah, because if it's something in my field, I'm gonna be like more interested in it.
Sure, yeah,
so I'll try to bring
Is that like a complete paper already? Or something that you're working on?
No. It's like